Thank you very much for the invitation. It's a really nice excursion yesterday to remain in my mind, in my memory for the whole life. Okay, I will, this course will concentrate on determinantal point process, and this first one, today the lecture will completely be a warm-up lecture. So I hope everybody will be warmed up and so that you can go to the lake this afternoon. Okay, so I will first give you some examples. Several different examples, a priori there's no relation between them. So the first example is we consider random matrices as the following. We're given any integer positive. We let xn to be n times n matrices with coefficients as random variables, such that this permission matrix and xii, the diagonal ones, and the up diagonal one, mu xij, and the image part are independent. Such that, let me write, please. They are independent and, okay, IID standard Gaussian distribution. And we're interested in the spectrum, the eigenvalues, let us say, of this xn. Of course, this matrix is a random matrix, so the eigenvalues is random set. And we're particularly interested in the asymptotic behavior of these eigenvalues. Of course, since the matrix is random, we have random things, but we studied the typical eigenvalues. Okay, we give it a name, later we will come back, GUE, which is abbreviation of Gaussian unitary ensemble. Ensembles, in fact, because we have many n. Unitary is because the distribution is unitary invariant. You can multiply conjugation by a unitary matrix, then the distribution will be stable. Okay. Our second example. So we will have a theory to describe it, but let us wait a bit. Our second example is the following. We consider the following function, random function. G and M. This such that this G and are IID with complex Gaussian distribution. So we have a holomorphic function whose coefficients are just Gaussians with standard Gaussians. So almost surely the radius of this series will be 1. So this almost surely defines holomorphic function on the disk. And we are interested in the zero set of this function. Those z in the unit disk such that n equals to 0. Since the function is random, of course, this is a random set. And we are interested in the description of such a random subset of the unit disk.
Why are we interested in the zero set? What is the relation to what was before?
To this?
Yes.
You will see.
Ah, okay.
They have the similar structure. Okay. It's kind of, I will give you several delicious cakes, and if you like it, you can try to learn how to cook it. Our third example is the following, which is started in the representation theory. How to say? Okay, I've got to give it a name. This is the zero set of GAF, which means Gaussian analytic function. Usually it's a GAF on the hyperbolic disk. Okay. The third one is the following. We consider random Yann diagram. The following random Yann diagrams were given a parameter theta. We want to give a probability on the set of all Yann diagrams of any size. So we will give a probability on so Yann diagrams is in bijection with the partitions of integers. We'll give it in this way, minus theta times dimension and to be careful and check the formula. Yes. So you see, here the partition corresponds to an irreducible representation of the permutation group of all the size of the partition. You're not supposed to know, I think it's classic. but so here is if we forget this and let this size of the partition to be fixed n, then this is the classical Blanche-Heller distribution on the partitions. And this is something called Poissonized Blanche-Heller measures. And with this, we will associate every Yann diagram. Let us draw the Yann diagram in the Russian tradition, Russian convention as follows. Here.
Could you say one more time what is lambda?
Lambda, so we are given n. So lambda is lambda 1, lambda 2, lambda certain I, such that terminates every lambda I is positive, and we have only finite number of non-negative integers here. And so if you see from here, here is the number of blocks here is, okay, we can see this number of blocks here is lambda 1, lambda 2, lambda 3, lambda 4. And this is a parameterization of diagrams like this. Is that okay? Okay, okay, this is the third case. You can, if you like the two cases, it's okay, it's sufficient. So we will associate each Yann diagram to a configuration on this side. So we have this. If there's a how to say, descent, then we think there's a point here. If it continues, this point here, a point here, and a point here. And now there's a rise here. Then there will be a hole. And here it's a point. Here is a hole. And etc. So this means we have mapped the set of all Yann diagrams to the configuration. Let me write it like this. If it's a point, I would say it's 1. If the hole, it's 0. So this probability and theta will have a push forward to certain probability.
What is this? Sorry, where did you map the set of Yann diagrams to what?
So the Yann diagram will, so you see here, this is one Yann diagram.
Yes.
And I will associate it to this one. Will associate it to the set of infinite to 1. And when there's a rise, there will be 0, and in this way. So it's a set of these, a point of this set.
Binary sequence.
Binary
So
sequence.
this is just a notation for infinite binary sequences?
Yes, yes.
2 to the power z plus 1/2?
Yes, because this our put it to the center of this. Let me just draw two blocks. So this one, the projection to here is minus 1/2.
So this 1/2 is completely without importance.
Yeah, okay.
It's a convention introduced by Vakshika Okenkov, I think. Okay, now let us turn to the formal introduction. Definition. We will consider certain set, which is magic, locally compact, and second countable. In short, it's a Polish space. So in our lecture, you just think E to be Euclidean space ID, CD, or the unit disk, or the lattice Z to the power D. And we will fix a Borel measure on this E. Here it will be Lebesgue or weighted Lebesgue, and in the discrete case, usually we fix the Conti measure. And we will write the space of configuration. Okay, this E will later be called phase space. The space of configuration on the phase space is defined as the subset of E, which is discrete. Discrete subset. There is no accumulation point in any. The only accumulation point can happen is the boundary. For example, is that clear?
Just not clear, not visible what is written. X subset
X
of E.
is a subset of E, and X itself is discrete. So, okay. So we're interested first what is called point process. So a point process on E is just probabilities, random probabilities. I will not say about the Borel structure on it, but let's just, it's not that important. Random probability on this space. So a point process, by definition, it's just a probability on space of configuration. So giving you a point process means giving you a method of choosing randomly the configuration from this space.
Just 1 second, Yanqi, Radon, so who is Radon? which object? To which object you apply the word random?
To the measure.
Measure.
Which one?
Okay, let me say Fourier. Okay. We can give it magic.
What
Fourier. So
This is safer.
the Fourier the sigma algebra, the Fourier sigma algebra is generated by the points of the of a configuration in sequence of finite windows. But
So
we will turn it back. But intuitively, what do you think point process? So theoretically, it's good to think point process just as a probability on this spatial configuration. And intuitively, you should think give you a point process means give you a random configuration. So it's just you have a random configuration. So now let's go to the first mathematical object, probably. The correlation function. So the first question is how to describe such a random configuration. Now I define this B to be the following function. We send a configuration which has a discrete set of D to the number of points inside this set D. Given B a bounded Borel subset of E. We can of course define such function. And in fact the Borel structure is induced by all is there such that all such function is measurable. Intuitively, to describe a random partition, to suffice to describe B1, Bn, the joint distribution of all such n tuples for this joint subset of E. So if I give you a random partition, a random configuration, how to describe it? You just fix several, this is not fixed, so you can take all possible ways of disjoint subsets. You just study the points inside every subset, and you study the joint distribution. Then this will completely describe the this random configuration.
So for all possible choices of n,
And
and
all possible
choices
choices of
subsets?
Bi. It's okay? So now if I have this So, if this is true, if there is a function rho n is a function of e to n to r, and this holds for all choice of disjoint BIs. Then we will say that rho n is n's correlation function of this point process, which is the probability measure on the space of configuration. Well, this is not intuitively evident. The intuitive definition is the following. Intuitively, we have the following. Is the limit of the probability of having one particle in, let's say, the ball I divide by the measure, product So, having one particle in this ball, centered of this fixed xi with radius epsilon. So, in some sense, the nth correlation function is a certain density of certain object.
So this the right hand side depends. So it's the same for every I, or I don't understand. The numerator and the right hand side is dependent.
I equals to 1 to n.
It's an infimum. What is it?
This epsilon tends to 0.
The probability of having one particle in one of those.
In each of them.
In each of them.
In each of them.
In each of.
So it's because probability of having two or more particles is infinitely smaller, much smaller.
Say that again.
So you write probability of having one particle because probability of having two or more is much smaller. Or
at least for determinantal point process, we will see that almost surely it happens. Yeah.
No, but this is actually general. No, this is actually general. This is why a correlation function exists.
Okay. Yes.
so it doesn't matter to write one particle or at least one.
I think so, but in fact, in a paper in Shiha Takatashi, I think they said for two more particles, it's little o. Yeah, probably. Yeah, exactly. But they have such an assumption, kind of. This is correlation function. Okay. So now we can divide the point process in several classes by the particular form of their correlation functions. This is only introduction, so it's not very rigorous. We have okay. We have certain 4 classes that will probably be okay. Let's compare them. The first class is Poisson point process. I will return back to it. Just intuitively, what is Poisson point process? You see here we have some random configuration. We have certain subsets. One, and the Poisson point process is those point process such that the number of particles inside the disjoint subsets I are independent random variables. So there's no interactions between disjoint windows. We will call these subsets as windows. This is not what we were going to talk about. Okay, let me write 3 because I will not talk about that one. Determinantal point process. Let me first skip the formal definition. This will be our main project. But okay, determinant point process. So what I give you the 3 examples that they are all determinant point process. And okay, I will give you the definition now. So the determinant point process, a determinantal, let me write it in short, a determinantal point process with correlation kernel K. K is a function on the product space. Is by definition is a point process such that the nth correlation function rho n is given by exactly the determinant of this matrix. Okay. For any n. Sorry. So the definition is clear? I hope more or less.
What okay for the 3 examples?
The first, I will return, for example, back to the GUE. The kernel will be answer Christoph kernel correspond to the projection to the first nth orthogonal polynomial, which first n Hermite polynomials. And the second GF Gaussian analytic function corresponds to this K is the Bergman kernel on the disk. And this random configuration, the kernel is I think which is called what? Gamma kernel? Some specific name, but it's not classical. So this is started by Grigory Olshansky and Okenkov and Borody.
And independently Johansson.
Okay. Just to complete these three classes, we have also Fathian process. Which is in fact of many open problems. If you like it, probably you can start it. Fathian process is the same thing, such that the configuration, the correlation function is given by certain Fathian. Fathian's certain kernel. I will not give you the formal definition of a Fathian, but you can think of the following properties is interesting. Fathian is defined for skew symmetric matrix, and the square of the Fathian is the determinant, the usual determinant. Okay.